Hello and welcome to lecture 8 of the course Microelectronics Lab. In this theory module, we are going to talk about RF characterization. We'll give you an overview of RF characterization and the challenges. We'll talk about RF measurement setup, instruments and accessories involved. The key equipment of all RF characterizations are a vector network analyzer. We'll talk about the working principle of vector network analyzer or VNA in short. We'll discuss how do we calibrate, why calibration is needed and how it's done. Then we'll talk about a different set of measurements, RF measurements one can perform, how do you process the measured data, and how do you de-embed the RF characteristic out of the measured data. What's the theory behind this de-embedding?
The term radio frequencies is generally used to refer to the 30 kHz to the 300 GHz region in the electromagnetic spectrum. This region is also further divided into smaller bands, and each of these bands find use in different applications. These bands are as defined by the International Telecommunications Union. An example of one such band would be the ultra high frequency band or the UHF band, uh, whose frequencies are between 30 megahertz and 300 megahertz. So the UHF band finds use in radio, and it also in past was used for analog television communication in many parts of the world. Another example of a band would be the SHF band. The 3 gigahertz, it varies between 3 gigahertz and 30 gigahertz and is used in cell phone communication and radars. So all these bands find use in different applications. To be able to properly generate, transmit, receive, and process signals at RF frequencies is thus critical because these RF frequencies are used everywhere today. New candidates such as gallium nitride based HEMTs and graphene based FETs are being considered as alternatives to current technologies and are being investigated extensively throughout the world. Once these devices are fabricated, so during investigation, when these devices are fabricated, characterizing them at these frequencies is necessary to ascertain the functionality and to make sure that they are working as expected in the frequency ranges that they're being designed for. So this presentation aims to give an overview about on-wafer RF characterization, which, as it turns out, is very different from DC characterization, and it comes with its own set of unique challenges. While performing DC characterization of devices, one need not worry about the inductive and capacitive parasitics associated with the setup of the DC measurements, because at steady state, such reactive components would play no role and thus they will not have an effect on the output. Only the resistive losses that are a part of the cable, either the small resistance of the conductor or the large but finite resistance of the dielectric present within these cables. So such resistive losses in the cables and other unwanted resistances inherent in the setup, their effects will have to be removed from the measurements. 4-wire measurements, as seen in earlier presentations, do exactly the same. Apart from the difficulties presented by DC measurements, characterizing at RF frequencies comes with its own set of difficulties, especially at the higher frequencies. Just performing a measurement of the currents and voltages at these frequencies is challenging. While performing DC measurements, however, we may have taken our ability to measure currents and voltages for granted. However, at RF frequencies, it is not so obvious. It is far more complicated to measure currents and voltages than it is to measure power at these frequencies. So often the instruments that we use measure power instead of measuring currents and voltages. 2. The reactance and capacitance associated with the cables, they respond to the RF signals. So what happens is that the cable, whose role is just to carry a signal from one end to the other, that itself begins to contribute to the response as seen by the measuring instruments. So not only does the measuring instrument see the response of the device, but in addition to it, it also sees the response of the cable. And it is not only about the cable, but anything else that is a part of the test setup as well. That too contributes to the final response as seen by the measuring instrument. So for example, the connectors too can contribute to this. Um, and it is not only about the accessories and the things that are part of the test setup, but also the other parasitics that are associated with the fabricated device. For example, the large pads and their pad capacitances, that too contributes to the final response that the measuring instrument sees. So needless to say, we need to have a way to measure, um, to remove the effect of the cables, connectors that are part of the test setup, their response, and also to remove the effect of things like the pad parasitics. So, faulty cables or cables that are just bent a lot, faulty connectors or connectors that have been connected loosely, not tight enough, these may lead to huge errors in the measurements. To add to the complexity of the challenge, the aberrations due to the bent cables, improper connectors, devices pad parasitics, these are not uniform for all frequencies. So at different frequencies, the response of the connectors, cables, the pad parasitics will be different. So we have seen in the previous slide that it is not always easy or convenient to measure currents and voltages in the RF domain. Rather, it is challenging, and it is extremely costly to have equipment which can perform these current and voltage measurements. However, it requires less complex hardware and thus less cheaper hardware to measure powers, and that is exactly what is usually measured when we do RF characterization of linear devices. So it is most convenient to obtain data as S parameters for linear devices. So using S parameters, we can obtain many useful information about the devices that are being measured, such as the cutoff frequency, or which is the unity current gain frequency obtained from the 0 dB crossing of the H21 curve, and the maximum oscillation frequency, which is the frequency at which the maximum power gain is unity. And we can also obtain input and output impedances and other important parameters from the S parameters that we obtain. So S parameters are essentially a way of representing how much of the incident power gets transmitted and how much of it gets reflected back from the same port. So it relates to these power ratios. The S parameters, they relate to these power ratios in a very specific manner, as we may have seen while studying about network analysis. In this slide, we describe the instruments and accessories that are a part of the test setup. So amongst the instruments, we would require a vector network analyzer, or what is known as a VNA. We will need appropriate cables and connectors. We will need probes, probe positioners, and a probe station. We will also need a calibration substrate and calibration software, and we will require a bias supply. All of these individual accessories and components are examined in greater detail in the slides to come. To analyze the response of linear networks in the RF regime, instruments known as network analyzers are used. These days, a single network analyzer can excite and measure the response of the connected network. To analyze a two-port RF network, a two-port network analyzer is sufficient. Traditionally, network analyzers are used to measure S parameters. All the modern network analyzers can do that and much more. Network analyzers are of two types, scalar and vector network analyzers. While the SNAs or the scalar network analyzers only measure the magnitude of the incident, reflected, and transmitted waves, VNAs measure the magnitude and the phase. So the complex values of the signals are obtained by the vector network analyzer, thus giving complete information. A natural consequence of that design is that the VNA is usually far more complex than that of an SNA. So to completely characterize a two-port network, port 1 sweeps the frequency with port 2 matched and obtains the S11 and the S21 parameters. Similarly, the S12 and the S21 parameters are obtained when the port 2 sweeps across the different frequencies with port 1 matched. So these two sweeps provide complete information of the S parameters of the device that are being characterized. Shown here is a keysight VNA. Specifically, the model is PNAX N5247A and is taken from the Keysight website. And on the right side, we see a representative schematic of a network analyzer that is taken from the IET Microwave Measurements book. So we have a single source two-port version of the same VNA at ANCF. Let us look at the working of the VNA in a bit more detail in the coming slides. And in the schematic shown, the source, the signal separation stage, the receiver stage, and the processing and display stage are together present in a VNA. The cables, duties, and accessories are not a part of it. We will now consider the role of each of these individual stages that I mentioned and some design choices for each stage to understand some terms which were used in the demonstration. So the first stage was the source, and the signal source provides the stimulus to the test system. So traditionally, the network analyzers used to come with a separate unit to provide the source. However, modern VNAs have the source integrated into the VNA. So the source is usually a voltage controlled oscillator, a VCO, or else a synthesized sweeper. So after the signal source stage, we have the signal separation stage. So let's assume that port 1 is being excited at a certain time to calculate S11 and S21. So one will have to know not only the power of the incident wave, but also the power of the reflected wave to calculate S11 and the power of the transmitted wave to calculate S21. Thus, separating the three waves is necessary to obtain the S parameters. The signal separation stage does this. This stage has three important functions. One, to separate a small known fraction of the incident signal to provide a reference for ratioing. Two, to separate the reflected component of the wave and to take out a small known fraction of it to provide to the detector. And three, to do the same with the transmitted signal. So how are each of these functions realized? So function 1, which is to take small known fraction of the incident signal, is done often by either using a power splitter or a directional coupler, and function 2 is done with either a directional coupler or directional bridges. So here in the slide we have schematics of the different hardware options we have for the signal separation stage of the VNA. So we will talk about function 1 first, which is to separate a small finite portion of the incident wave so that we can measure how much power is really present in the incident wave. The choice of the hardware for doing this can either be a power splitter or a directional coupler. So the advantage that the power splitter has is that it can operate over a wide range of frequencies, but it suffers from the drawback that the power given at the output of the power splitter is far lesser than what is given to it at the input. This is because it is a resistive device. And in the best case, when everything is matched, we will have about 1/4 of the total power given to the power splitter appearing at its output, and thus the test port of the VNA. However, if we were to use a directional coupler, we would have the advantage that the power loss is minimum and very small fractions of the total power can be drawn out and separated for the next stage. But it suffers from the fact that it cannot perform well enough in the lower frequencies, and you cannot expect very wide bandwidth from directional couplers. So that is about function 1. And when we are talking about function 2, which is the task of separating the reflected wave from the incident plus reflected wave that we see at port 1, and measuring how much power is there in the reflected wave. So to do this, we can either make use of a directional coupler or we can make use of directional bridges. So directional couplers we would consider ideal because they have necessary directional properties. So it means that in the forward direction, when whatever wave is incident, it reaches the opposite arm with very minimum loss, and it offers good reverse isolation. However, owing to the difficulty that making very broadband couplers is hard, directional bridges are often used. Bridges can operate over a very wide range of frequencies, but they exhibit more loss. They work by producing signals that are proportional to the mismatch of the device connected at the port with respect to the nominal port impedance, which may be about 50 ohms. The direction shows all branches to be around 50 ohms, but if we want more power available to the test port, the resistance on the other branch can be increased. It's a design choice for the person who's making the VNA. So for network analyzer, one has an option to either use diode-based broadband detectors or tunable narrowband detectors. The limitation of the diode-based broadband detector is that it is incapable of detecting the phase of the signal input. Thus, VNAs, which by definition should measure the phase as well, cannot use diode-based detectors. The alternative is to use tunable narrowband detectors, and it is used for VNAs. So tunable detectors use a mixer and down convert the high frequency signals to signals of an intermediate frequency, and this intermediate frequency is essentially the difference between the frequency of the RF signal and the frequency of the local oscillator. The intermediate frequency, which is essentially a bandpass filter, the IF filter, which comes after the mixer, is essentially a bandpass filter of user-defined bandwidth, but is centered around the intermediate frequency. So the purpose of having this bandpass filter or the IF filter over there is to reduce or remove all harmonics and spurious signals that come from the mixer and the harmonics which may have been generated by the source itself. So it is important to note that the bandwidth of this IF filter is user defined, meaning that at the time of usage of the VNA to perform measurements, the user will have to specify the bandwidth that he or she wishes to use. A natural consequence of such filtering is that the noise also gets reduced. The noise of frequency components beyond the IF bandwidth on either sides are not allowed through the filter. It is so it also means that if the IF bandwidth is smaller and narrower, the noise in the measurement is also that much lower. So reducing the IF bandwidth also increases the dynamic range of the receiver. The dynamic range is a measure of the range of signal power the network analyzer can measure with errors within tolerable limit. Averaging 2 is another method that we can use to reduce the amount of noise in the final output. However, increasing the number of sweep averages per measurement or reducing the IF bandwidth can slow down each measurement considerably. So we need to be careful about choosing these parameters such as the IF bandwidth and the number of averages that we want um, per measurement. So another obvious way of increasing the dynamic range is to increase the input signal power. So we'll have to keep these in mind when we're defining the test conditions of the before we start the test. Okay, so shown on the left in the slide is a very simple schematic of a single source 2-port VNA which can be used to perform simple S parameter measurements. While measuring S11 and S21, the source can be connected to one of the power splitters, and when measuring S22 and S12, the switch can be in the other position. So we see that at the signal separation stage, we see that as a part of the signal separation stage, we have a power splitter at the input right after the source, and we also have directional couplers that are present near the ports of the VNA in this diagram. So the figure on the right, however, is a block diagram of the Keysight 2-port VNA. It's called the PNAX model. The VNA has two sources marked as source 1 and source 2, which may be useful in some kinds of measurements, but is unnecessary in regular S parameter measurements of 2-port networks. To be able to use source 2, one would have to get the same installed and the same kind of circuitry that is associated with test port 1 and test port 2 as shown in the diagram. The same thing should also be available at source 2 output 1 and source 2 output 2 as labeled in the diagram. Then after getting that, the VNA would then be a 4-port VNA. So modern VNAs can do more than S parameter measurements such as noise figure measurements, and thus we see those blocks as well. However, these blocks, the blocks which have been discussed so far, can be spotted within this diagram. So we have seen in detail about the VNA and the internal structure of the VNA and some important parameters that we'll have to set while using the VNA. We can now move on to the other components and elements that are a part of the test setup for RF characterization. We will now take up cables and connectors. So for RF measurements, to route the signal from the VNA to the probe tip, typically coaxial cables of different types can be used. A good coaxial cable has a well-shielded inner core, and the insertion loss should be minimum, and the phase and amplitude stability of these cables should be high, and they should be reliable. The distance between the probe tip and the VNA port should be kept as minimum as possible to avoid any unnecessary losses in the cable. So all cables must be handled carefully, since repeatedly bending the cable beyond a certain acceptable range or acceptable number of times can damage the inner core and sometimes the shielding. So using abruptly bent cables will show up in the measurement outcomes and it will affect signals of different frequencies in different ways. So there are three main types of cables that we can use for in such a setup. One, we can use flexible cables, or we can use semi-rigid cables, or hand formable cables. So we will discuss all three types of cables now and the differences between them. So flexible cables, as the name says, are flexible. You can move them around and they don't offer resistance to movement that much, but it does not mean that we should move it too much as well. So we should not bend it beyond a certain range, and we should not manhandle it at any cost. So because even though they are flexible, they have a certain lifetime, and um, they should not be manhandled, exposed to heat or water. So since flexible cables have braided copper or silver typically as the shield, bending it too much may cause the shielding to loosen. Also, exposing the cable to water can alter the electrical properties of the cable. When the cables are exposed to heat, what will happen? The dielectric, which may be made out of plastics like polyethylene, may begin to soften and yield way for movement of the core, which may affect the properties. So these type of damages must be avoided not only for the flexible cables but of cables of all types. So the next type of cable is the semi-rigid cable. So while for flexible cable there was either braided copper or silver, semi-rigid cables typically use copper or aluminium. And the thing about semi-rigid cables is that once it is set, the shape cannot be changed without damaging the shield. The advantage of semi-rigid cables is that it offers better shielding than the flexible cables, because over here the shield is not braided. The insertion loss of such cables is also minimum in comparison to the other types. So there is another type of cable called the hand formable cable, which is of intermediate rigidity and insertion loss. So it's not as rigid as the semi-rigid cables and it's not as flexible as the flexible cables, but also the insertion loss is somewhere in between the insertion loss of these two types of cables. So such cables may, for example, have a tin-filled copper outer conductor braid to achieve hand formableness. The connectors given at the end of cables and other accessories need to be precise, and we need to make sure that they remain that way. There are different types of connectors, and some standard definitions are given by IEEE. The inner and outer diameters of the connector, the dielectric used, the connection mechanism, the length of the pins, and any other geometrical parameters are defined by the standards. Although this slide names only 2, there are hundreds more that could have been named. So some issues that may be present with the connectors are as follows. The pins which carry the signal are meant to lock and are meant to lock with the other one, may be undersized or oversized, which affects how well they contact with each other. So two connectors which are meant to contact with each other, one male and one female, if they do not fit exactly, if the dimensions are not exactly as described by the standards, then it may not form a contact well enough with each other, so that may cause issues in the measurements. So the non-concentricity of the pin with respect to the outer shield is another fault which may often be present with the connectors, and no connector provides exactly the same characteristics when connected over multiple attempts. But good connectors though offer, the difference is not too much. So these are things that we can check for when we are trying to test cables and whether they're good. So the third important component or element of an RF test setup would be the probe. Probes are what physically contact the device pads and provide excitation to the DUT or absorbs the signals transmitted or reflected from the DUT. While in DC measurements, we were simply able to use single probe tips. Doing so for RF measurements would not be possible. The coaxial cable's core, while carrying this signal, the outer layer is the reference. The signal as well as the reference must be supplied to the device. So a probe used for RF measurements will have at least one ground and its signal contactable tip separated by a fixed distance. Both will be present in the same probe. So these are called either GS structures or else they can be called SG structures. And they have a drawback though, and the drawback is that the field fringes too much in them. Also, to reduce the capacitance between the ground and the signal probes, another ground can be added next to the signal probe, thus forming a GSG structure. This has the effect of reducing the capacitance, but also the amount of fringing of field which happens to the chuck. Another drawback of the GS probe is that one less ground probe means less shielding, resulting in crosstalk problems. GSG probes are typically helpful while measuring at higher frequencies. So while fabricating the device, we need to keep in mind the probe pitch, and so that the probe pitch and the device pitch match, and we can exactly probe the device with the GSG probes we have. So depending on what material the probe is made of and how well it is made, it will be repeatable. So we need the probes to work repeatably. So we need to give the same kind of contact every time we probe the device. So if we know that we're going to perform measurements on these transistors to check their amplification behavior in the active region in the common source configuration, even before we fabricate the device, we can make it such that the gate terminal comes in, the pad for the gate terminal comes in between the pads for two source terminals on one side, and the pad for the drain terminal comes in between pads for the two source terminals on the other side. So this way, when we contact the GSG probes on one side, we will be exciting and measuring the gate, and on the other side we will be contacting and measuring the drain, and the source will be kept at ground. We will now look at measurement calibration. So the word calibration would refer to doing something in order to remove much of the inherent errors in the system. There are two types of calibration in this context. One is measurement calibration and two is called instrument calibration. So to ensure that the VNA is functioning according to the specifications, once every few years, the VNA is sent back to the manufacturer so that they can perform calibration on the internal structures of the instrument. This is known as instrument calibration. However, there is another kind of calibration which should be done to separate the effects of the junctions, connectors, and cables. Measurement calibration, henceforth we will refer to it as just calibration, is the process of removing the effect of the systematic errors inherent in the measurement setup from the VNA to the probe. So in this process, the setup itself is characterized for its response to certain known standards such as opens, shorts, and loads. It is done once before every set of measurements. So there are different kinds of errors which can affect the RF systems. So we would broadly classify them as systematic errors, random errors, and drift errors. So only the systematic errors can be removed from by performing calibration. So I'll name a few errors now. The errors are directivity, isolation, source mismatch, load mismatch, and frequency response. So I'll just explain a bit more about each of these kinds of systematic errors that may be present within the VNA and the test setup. So the first one is called directivity, and it is basically the inability of a directional device, such as we spoke about the directional couplers which are present within the VNA in the signal separation stage of the VNA. So the inability of such directional devices to properly separate incident and reflected signals entirely is what leads to this error that we call as directivity. The second error that I mentioned was isolation. So there may be a leakage of energy between the net analyzer signal paths, and that contributes to an error in the transmission measurements, much like directivity does in a reflection measurement. The third type of error that I mentioned is source mismatch. So the wave reflected by the DUT is reflected at the source port once again. So the wave that is incident upon the load, some part of it gets reflected, and because of an improper match or because of a mismatch at the port, some part of it may get reflected once again. So we need to account for that as well, and that is called source mismatch. And there is similarly load mismatch, which occurs at the load end. And the last type is called the frequency response or tracking. So a way to reduce random errors, so that this was about the systematic errors, and to we can remove these by calibration. However, if you want to reduce the random errors, one of the ways is to do that is by averaging consecutive readings. And to avoid drift errors, the only thing one can do is just to wait for the system to start and warm up before actually doing the calibration. We had noted in one of the introductory slides how the response measured by the VNA is not purely the response of the device, but also the response of the cables, connectors, and all other accessories that are on the path to and from the DUT. We had noted the need to remove the effect of such elements in order to correctly obtain the response of the DUT alone. This happens in the calibration stage. It is important to remember that calibration is done with the help of standard structures whose characteristics are known beforehand. The calibration algorithm finds the response of the test setup by comparing the expected response of the standards with what the VNA actually measures. As stated earlier, the calibration standards you have the calibration standards you have available will determine the kind of calibration algorithm you can use. SOLT algorithm, for example, uses the short, open, load, and through test standards to correct for the systematic errors. Similarly, the TRL algorithm uses the through, reflect, and line standards. Since not all shorts and throughs are the same, we cannot use any short and any through we like. We ought to use the ones that are provided by the company, previously characterized, and whose data is stored within the calibration software. All these standards come in either a calibration kit or a calibration substrate if all the calibration standards are present on the same die. SOLT algorithm, for example, requires precise standards in probing. However, TRL and its advanced versions are relatively tolerant to the same. This makes manufacturing the calibration substrate for SOLT harder. Seen here is a calibration substrate by Cascade Microtech. So here we see in the first red box, we see one set of through, short, and load standards for SOLT calibration. We have alignment marks which are used as reference while probing. The calibration substrate also provides some transmission line structures, and it provides a metallized area that we can use to perform the theta correction and planarize the GSG probe tips of the probe. The process of calibration removes all possible systematic errors till the tip of the probe being used. All systematic errors till there are accounted for. Thus, we say that the plane of reference is set to be till the probe tips for the measurements after calibration. However, we would prefer to remove the effects of the pads too and move the plane of reference closer to the device. We will see how the effects of the big pads will be removed in later slides when we discuss de-embedding. WinCal is a software which can be used to perform calibration. Stored in the software and accessible to it are all the data about all the calibration substrates provided by the same manufacturer. It also has the ability to perform many different calibration algorithms. If we are interested in the amplifying behavior of the transistor, we will have to provide DC voltage to fix the operating point of the devices being measured while performing the RF measurements. Extra connections are required to make this happen. SMUs will have to be connected to the same GSG pads to bias them. However, we will not use extra probes to probe the same pads. Instead, we can provide both the RF as well as the DC voltages to these devices through the same GSG probes. To make this happen, we will need a special accessory known as the bias D. One input of the bias D can be the RF signal and the other input the DC signal for biasing. The third and output terminal of the bias D will give a superposition of the DC and RF signals that were given to it as an input. The S parameters of each device at all frequencies required can be measured at a given Q point. The same can be repeated at as many Q points as required to characterize the device completely. The device must be probed deep enough to give meaningful signals while not damaging the pads too much or without accumulating too much of the material on the probes. The VNA can display the S parameter data in many different formats, including but not limited to magnitude, that is in decibels versus frequency, and also in Smith charts. Each measurement data can be saved in many different formats. It is standard to save it in the touchstone formats though. This is the format which is widely used and recognized for RF measurements. Further processing on the obtained data can be carried out in another system with any software of our preference. MATLAB has a separate RF toolkit, and so does Python. They both can read the touchstone files as they are without any editing, and the module name, which allows us to read touchstone format files in Python, is called the scikit RF module, and any further processing to extract any further information from these S parameters at different frequencies can be carried out by writing a script. However, if using CSV files or any other format is more convenient, the VNAs also support saving it in the CSV format or the other formats as well. We had earlier noted when we discussed calibration about how performing calibration moved the plane of reference from the ports of the VNA to the tips of the probe. However, we also noted that the parasitics associated with the pads, the large GSG pads that were fabricated along with the device on the die, leads to unwanted effects and the parasitics associated with it does not provide a true picture of the characteristics of the fabricated device alone. So we need to remove the effect of these large GSG pads on the data. This is an important part of processing the data that is obtained from doing the measurements. Such data has the effects of the pad parasitics embedded into it. The process of removing such effects is called de-embedding. So VNAs may offer options to directly de-embed data. Alternatively, we can perform de-embedding ourselves by writing scripts. Post de-embedding, other data can be obtained from S parameters. For example, the H21 magnitude and phase with which we can calculate the FT. There exist many ways by which one can de-embed the measured data and make it free of the effect of the unwanted pad-related parasitics. Different kinds of structures, which contain no active devices in them, are used to characterize the different parts of these pad parasitic networks that are associated with the pads. So opens, shorts, and through test structures, or a subset of them depending on the requirements of the de-embedding method that we are using, are used for this. Pads of these structures and the pitch are all the same as any of the other devices, and are fabricated along on the same die which contain the devices. So based on the model that we have assumed for the parasitics, one can mathematically remove the effect of the Z parasitics from the measured DUT data. In this slide, we are going to discuss a bit more about one particular de-embedding method that is known as the open-short de-embedding. So this uses, as the name suggests, only the open and short de-embedding structures. The model that is used for the open-short de-embedding assumes that the transistor or the device is in series with certain impedances, and the whole network is in parallel with another set of admittances, as shown in the figure. So the data that we have obtained from measuring the device along with the pads is modeled as shown in this figure. We observe that the ZLI notation, that is the ZL1, 2, 3 notation, is used to indicate the network that is in series with the actual device, and the YP 1, 2, 3 is used to indicate the parallel admittances in the network. If the active device wasn't present in the network and instead there were an open or short in its place, we would have the following networks as shown on the right side of this page. On the top we have the network we would have if there was an open in the place of the transistor, and at the bottom we have the resulting network if there was a short in place of the transistor. These two networks are used to model the open and short de-embedding structures respectively. We can recall at this stage that any two-port networks, when combined in parallel, gives an other two-port network whose Y parameters is the sum of the two individual Y parameters. So when the Y parameters of a two-port network is subtracted from the Y parameters of a network in which it is present in parallel with another network, we get the Y parameters of the second network. Thus, if we were to subtract the Y parameters of the open network from the Y parameters of the DUT model that we had assumed, we would find ourselves with the Y parameters for a network as shown on the bottom left. And if we were to subtract the Y parameters of the open network from the Y parameters of the short network, we would be left with a network as shown on the bottom right. By writing out mathematically, we can see we would easily be able to prove that the Y parameters of the transistor alone is given by the expression as shown below. So after having performed calibration, measurements, and then de-embedding, only then do we get the real response of the device alone. So in conclusion, DC measurements and RF measurements are a world apart. RF characterization is far more complex, thus demanding far more precautions to be exercised. And we also need several special hardware components, such as well-working and well-maintained VNAs, special cables and connectors, calibration substrates, among other accessories that are essential to perform RF measurements. Calibration, de-embedding are necessary to obtain the real characteristics of the device alone, without the effects of the system or the parasitic networks. Although the measurements immediately give us the S parameters, after performing de-embedding, we can obtain a lot of different kinds of information about the device. Thank you.